Hello, my name is Mufei Li. I'm a PhD student in machine learning at Georgia Tech. I want to thank the organizers for the great efforts in holding this workshop. Today, I'm going to introduce LayerDAG, a new generative model of directed acyclic graphs, which may potentially benefit system and hardware scenarios. This is a joint work with my co-authors Viraj, Eli, Shanghai, Zhao Dong, Srinivas, Ying, Tusha, and Pan. Directed acyclic graphs, directed graphs without cycles, have broad real-world applications. DAGs can naturally depict data flows between operators in neural architectures. More generally, many computational graphs and intermediate representations take the form of DAGs, which play a critical role in optimizing compilers and circuit netlists. Given a collection of DAGs, we're interested in learning their distribution by training a neural network, which we call generative model. Once trained, we can use this generative model to generate realistic new DAGs. Generative models of DAGs may serve the purpose of obfuscation. In sensitive scenarios like system and hardware design, directly sharing the original data may be infeasible. A powerful generative model allows sharing realistic synthetic data instead, which helps protecting intellectual properties. In addition, many DAGs in system and hardware design are associated with labels like latency, throughput, bandwidth. In such cases, building conditional generated models of DAGs allows effectively searching the space of valid DAGs for design system metrics. To build generated models of DAGs, we can start with the simplest DAGs, namely chains or sequences. Nowadays, language model is the most important and successful generative model of chains. It is also known as autoregressive model, which iteratively generates the next word conditioned on the previously generated words. Naturally, we're interested in extending it to general DAGs. DVAE proposed an autoregressive model of DAGs based on topological orderings. Topological orderings are widely used for converting DAGs into sequences. In a topological ordering, if there is an edge from node U to node V, then node U must precede node V in the ordering. Given this DAG, an autoregressive model can generate its nodes and edges sequentially following a topological ordering, one node at a time. However, topological orderings are not unique. Even this small DAG has 3 topological orderings. To properly learn an autoregressive model based on topological orderings, we need to perform manual data augmentation, which can be cumbersome for complex real-world DAGs with a huge number of topological orderings. A natural question is then, can we develop an autoregressive model of DAGs with a unique generation ordering? Equivalently, can we obtain a unique partition of the nodes in a DAG? The answer is yes. Given a DAG like this, we can take iteratively the set of nodes without predecessors and then remove their outgoing edges. As you can see, this yields a unique partition of the nodes into subsets, which we call layers. In the context of language models, a partition of a sample is called tokenization. The Layerwise tokenization gives rise to a Layerwise autoregressive model of DAGs. Given a partially generated DAG, we first predict the number of nodes in the next layer. Then we can predict the node attributes. Finally, we predict the edges from previous layers to this new layer. We repeat this process for each new layer until the size of new layer is predicted to be 0. However, a challenge arises from the previously proposed Layerwise autoregressive model. To preserve the uniqueness of Layerwise tokenization, we need to simultaneously generate multiple node attributes or edges. This can be problematic, in particular for modeling DAGs with strong logical dependencies. For example, in a computational graph, the edges need to satisfy constraints like dimension match of matrices or a particular number of operands for a matrix operation. To tackle this challenge, we employ discrete diffusion for multiple rounds of refinement. Diffusion models have become the standard for image generation. For a high-level idea, starting from a real image, we can gradually add noise to it until we obtain pure noise that can be sampled from a standard normal distribution. Here, capital T is the number of diffusion steps, also known as the number of refinement steps. We can train a neural network, called denoising network, to perform one-step denoising. In other words, the neural network is trained to remove the noise added in the previous step. Once trained, we can sample pure noise from the prior Gaussian distribution and use the denoising network to gradually convert it into a clean image. Diffusion models have been extended to discrete data like categorical attributes and graph edges. Putting everything together, we have derived LayerDAG, the first autoregressive diffusion model of DAGs. For evaluation, we consider 3 real-world datasets for conditional DAG generation. The DAGs considered have up to about 400 nodes, which is an order of magnitude larger than the ones considered by previous works. TPU-tau is a collection of kernel graphs for machine learning workload on tensor processing units, with the DAG label being runtime average over compiler configurations. HLIS, high-level synthesis, is a collection of intermediate data flow representation graphs for compiled C programs, with the labels indicating the resource usage of lookup table measured on FPGAs. MLArch is a collection of neural architectures with labels indicating their inference latency on mobile CPU. By plotting the distribution of the layer sizes, namely the number of nodes in a layer, we can see that these distributions tend to be long-tailed. For conditional generation, given a collection of label DAGs like this DAG with label Y, we train a LayerDAG model to generate a DAG condition on its label. Performing ground truth evaluations for conditional generation in system and hardware design requires direct measurements on specific computation platforms, which can be costly or infeasible due to limited access. For example, the HL's dataset requires program implementation and measurement on FPGAs. Therefore, we turn to surrogate cost models instead, which have been widely used in applications like auto-tuning of compiler. Specifically, we use the trained LayerDAG model to generate synthetic DAGs conditioned on real labels. We then use the generated label DAGs to develop a cost model and evaluate the performance of the cost model on a held-out real DAG dataset. Assuming a strong correlation between DAGs and their labels, a better generated model will then lead to a better cost model. We report Pearson correlation coefficient as a metric for the cost models. On all 3 datasets, LayerDAG consistently outperforms the baselines, including existing autoregressive models of DAGs. For reference, we also include the metric of the cost models developed on real DAGs. On MLArch, we observe a negligible gap between the cost model developed on generated DAGs and the one developed on real DAGs. As we employ multiple diffusion steps for multiple rounds of refinement, we can potentially achieve a quality efficiency trade-off by adjusting the number of diffusion steps to use. Empirically, we find this to be an effective strategy and often yield a better or comparable trade-off against the baselines. Our implementation will be released in this GitHub repo. If you are interested, you are more than welcome to give it a try and provide suggestions for improvement. Thank you.